this bounded set B is going to be uniformly attracted by A as P goes to infinity, okay, in long run. So this is something that follows from definition where the B is bounded actually. Okay, for any bounded subset of H, or any bounded subset of H, since A is a global attractor, will be uniformly attracted by the set A as D goes to infinity. Are the all trajectories that starts from this bounded set will end up converging in the set A actually, in the global attractor A. Now if this is the case, then I can rewrite this statement as that then for every epsilon positive, there exists a T depending on the epsilon, such that for all T after this T that depends on epsilon, the distance between, all trajectories that starts from B and A is less than or equal to epsilon by 2. Okay? Is less than or equal to epsilon by 2. So what does follows from here? So what does this show? This shows that the all points, okay, the all trajectories, the distance between the trajectories and A, okay, the trajectories that starts from B and A can be made as much as small, what do you call, by epsilon by 2, okay, which is strictly less than, what do you call, epsilon. So hence I can say that each element of this ST operated onto B is sitting inside a ball of the radius epsilon actually. Okay, so it's sitting inside the ball of the radius epsilon, and if this is the case, indeed this is a subset of V epsilon. Okay, this is a subset of V epsilon, and hence the definition of the absorbing set is satisfied. That for any for any bounded set B, if you consider the trajectories that starts from the bounded set B, will end up in the absorbing set actually, will end up in the absorbing set. In other words, that ST operated onto B is going to be a subset of the absorbing set. So it satisfies this definition. Hence, you're going to say that all bounded sets are absorbed by the set V epsilon actually. Okay, so they are absorbed by the V epsilon. So if you have a global attractor, the epsilon neighborhood is really the absorbing set actually. So the interesting question would be, do you have other way around actually? In other words, if you have an absorbing set, can we construct a global attractor actually? The answer is yes. And here is the theorem that answers this question. Okay, and this will be the theorem that later we will employ, okay, to do the things in the concrete sense actually. Okay, so here is a theorem that provides a sufficient condition. Okay, so it provides a sufficient condition for existence of global attractor. Okay, so it provides sufficient conditions for a global attractor. For this result, we will assume that H is no more a complete metric space, but it's a special kind of a complete metric space. So it's a Banach space, HP Banach space, and S of T be a nonlinear C0 semigroup. Okay, so it's a semigroup on H that satisfies following condition. Okay, satisfies following condition. Satisfying following conditions. Okay. So the first condition is there exists an absorbing set B naught. Okay, so if you have an absorbing set B naught, and the second condition is that for any bounded set B, okay, for any bounded set B, we can always find an instant T naught that depends on this bounded set B, such that after this instant T naught, okay, the union of all orbits of B is relatively compact, actually. Okay, such that the union of all orbits of the bounded set B after the instant T naught is relatively compact in H, actually. In other words, that its closure is compact in H. So if these two conditions are satisfied, then you have an interesting result. Then there exists a global attractor. Okay, there exists a global attractor that attracts the all bounded subset in the boundary space. One thing. And this global attractor is something familiar. It is basically an omega limit set of the absorbing set B naught. Okay, is a global attractor. Okay, is a global attractor actually. So let's quickly see. So if you have a boundary space and a semigroup, and you have an absorbing set B naught, and this condition is true that for any bounded set B, you can always find an instant such that after this instant T naught, the union of the orbits is relatively compact in H. So if these two conditions are satisfied, then there is a global attractor that attracts the all bounded subsets in H, and that global attractor is nothing new, but it's an omega limit set of the absorbing set B naught actually. So if you can compute the omega limit set of the absorbing set B naught, that would be explicitly the global attractor actually. Okay, so this is what that would like to do. So here is little proof. If you remember, in order to prove that A is a global attractor, we need to show three things. We need to show that A is a compact set, okay, and it attracts all bounded sets in H. Okay, so these are the crucial conditions that it must satisfy. I'm saying this is the condition that you already have. Why? Let's recall a lemma that we proved when we were talking about the first category problem, or the theory of the omega limit set. So we proved this result. This result says that if you have a subset of H, okay, where H is some Banach space, then you can find an instant T naught. So if there exists an, so you have a non-empty subset of H, and if there is an instant T naught such that after this instant T naught, the orbits of A, okay, or the trajectories that starts from A, their union is relatively compact in H, then the omega limit set of this set A is non-empty, it's compact, it's invariant actually. Okay? And further, if A is connected, then omega of A is connected actually. So what we will like to do now, I would like to take the A as B naught. Okay? I would like to take A as B naught. Now the second condition is really this condition actually. Is essentially, this condition. Or that this condition is true for the bounded set. If the condition true is true, what does the condition two is telling? That for bounded set B, there exists an instant T naught such that the S of T operated onto those bounded sets is relatively compact actually. Okay? Now, this set B naught is also bounded actually. Okay? So there is an additional thing that this set B naught is this set B naught that we have assumed its existence is a bounded set. So if it is a bounded set, there must be an instant T naught such that S of T operated onto B naught is relatively compact by condition 2 actually. Okay? By condition 2. Because for every bounded set you have this. So this means that omega limit set of B naught, we already know that it's non-empty, we know it's compact, we know it's invariant as well, which is a part of the definition of being attractor. Okay? So you already have these properties actually. In fact, we will see that the omega limit set of B naught is also connected actually. Okay? So we already have the crucial parts, a lot of information about the set A actually. Okay? Because the condition 1 and condition 2 are satisfied. So therefore, this omega limit set of B naught, okay, is compact, it's non-empty, it's invariant, okay, which is an important part of being definition of attractor. So the only thing now that we have to show is that this A attracts the all bounded sets in H. So this is what that we have to just focus on. Okay. So what we would like to show, that A attracts all bounded sets, okay, in H. So that's what we would like to show. Okay. Now we will show this through contradiction actually. So suppose this is not true. Suppose contrary that there exists a bounded set, okay, B, such that it is not attracted by A. That is, that the distance between the trajectories starting from B and A does not go to 0 as T goes to infinity. Okay, so it is not uniformly attracted by set A actually. So if this is the case, what does it mean? What does it mean? So it means there is a sequence of times Tn that goes to infinity such that and a positive number delta such that the distance between S evaluated at Tn operated onto B and A is always bigger than or equal to this delta by 2, which is a positive number. Okay, which is a positive number actually. So in other words, we can't make these two sets closer than delta by 2. So there will be always distance of delta by 2 between them actually. And if this is the case, then we can also say that for every n, and there is Bn in B such that the distance between Stn operator onto Bn and A is bigger than or equal to delta by 2. Okay? You know, for all times. For all times Tn goes to infinity. So these are some of the, you know, the immediate consequences of the definition that you have, the assumption that you have, the supposition that you have made actually. Now, since B is a bounded set, okay, B is a bounded set, and I know that this B naught is absorbing set actually. So there are two things. If it is a bounded set, then it must be absorbed by B naught, and since it is a bounded set, by condition 2, there is an instant such that this guy is relatively compact actually. Okay. Now since we know that B naught is an absorbing set, okay. So for this bounded set, or the bounded set B, that for which we have these conclusion, okay. So for B, there exists an instant t1 depending on B such that after all instants, for all t bigger than or equal to t1, the S of t operated onto B, okay, the trajectory that starts from B will end up in B naught actually. They will always stay in what do you call B naught. So this is true for all t bigger than or equal to t1. Now in particular, since this Tn goes to infinity, okay, so the instants of time goes to infinity, so there will be an n, there must be an n, there must be an instant n, that after this instant the Tn will be bigger than or equal to T1 actually. Okay? So you can say that for large enough T, okay, so for large enough n such that Tn bigger than or equal to T1, okay, the instants of this sequence for which Tn is bigger than or equal to T1, this would still be true. In other words, I can say that S of Tn operated onto P is going to be still in B naught, because this is true for all instants after the T1 actually. Okay, after the T1. What is the immediate consequence of this? The immediate consequence of this is also that this Stn, the sequence Stn Bn, is also part of the B naught actually. Okay. Hence, therefore, I'm going to say that this sequence Stn Bn, where Bn are the elements of B, is a sequence in B naught actually. Okay. Now what is the condition 2? The condition 2 is that for any bounded set B, we can also take that bounded set to be B naught. There is an instant, after this instant, the union of the orbits of B, okay, is relatively compact actually. Okay. And so in other words, I can take this B to be in particular B naught. So the union of the all orbits after some instant, starting from B naught, okay, is relatively compact. So in other words, so this sequence which sits here, okay, is also relatively compact actually, okay, because this is going to inherit that relative compactness from here. So by condition 2, we can say that this sequence is relatively compact. And what do you mean by a sequence to be relatively compact? That there exists a subsequence that is going to converge. So if this is relatively compact in H, there exists a subsequence, okay, of this sequence that will converge in H actually. Okay, so there exists a subsequence. Let's again denote it by S of T and Bn. Okay, let's again denote it by S of T and Bn, such that it converges to a point, say eta in H as, you know, n goes to infinity. Okay, or Tn goes to infinity. Okay, as Tn goes to infinity. So this is what it is going to follow. And now consider the following. Now what is eta? Eta is limit Tn goes to infinity S of Tn Bn. Okay, and now I can also write this S of Tn to be S of Tn minus T1 plus T1 operated onto Bn. Okay, and if I apply the semigroup property S of Tn minus T1 operated onto S of T1 operated onto Bn. Okay, so this shows that this also converges to eta. Now I would like to recall the definition of omega limit set and then relate that definition by this last conclusion actually. Okay, I must write it here actually. See, for example, what do you mean by the omega limit set of B naught? So the omega limit set of B naught consists of those functions psi that are the functions of the space variable x, such that for which there exists a sequence T naught, Pn, and there exists a sequence Bn, okay, such that S of Tn, okay, operated onto Bn converges to, what do you call, S of Tn operated onto Bn converges to this element psi. So this is what the definition of the omega limit set is. Now, if you see, this is S of T1 operated onto Bn. This is an element in B naught actually. Okay, that's an element in B naught, or that's a sequence in B naught. For fixed T1, S of Tn Bn is a sequence in B naught. And if I call this sequence Tn minus T1 as, say, Tn prime, okay, so you have what you want. So Tn prime is, okay, so Tn prime plays the role of Tn, and this S of T1 operated onto Bn plays the role of Bn. So what does this statement is showing? That S of Tn prime operated onto this as a Tn, this Tn prime goes to infinity, converges to eta. So if you have this limit, then from the definition it follows that the eta belongs to the omega limit set of B naught, which is the global attractor A. Now this is really a straight contradiction with this statement. Okay, this is in the straight contradiction with this statement. This eta should not be in A, because the distance between that eta and A should always be bigger than or equal to delta by 2. So that's a straight contradiction. And since you have this contradiction, you're going to say that your assumption that you had in the beginning of the proof, that there is a bounded set which is not attracted by the attractor A, is wrong. So if that assumption is wrong, what is true? That A attracts the all bounded subsets of the Banach space H actually. So hence A is a global attractor. Okay. Hence A, which is the omega limit set of the absorbing set, is a global attractor actually. Okay, so this is what is really the proof of the result. Okay. There is a remark as well. It's a simple remark. I would like to see that. See also it's when you see the proof of this from the notes, that this omega of B naught in the which this attractor A is also connected. Okay, so if B naught is an absorbing set, then this is connected. Okay, because you can see that the B naught is connected actually, and then we know that we know from the previous lemma that I mentioned in the beginning that if A is connected, then its omega limit set is also connected actually. Okay, so you have the connectedness of the A as well. So this is what really is the key theorem that is crucial when you want to have the existence of the global attractor actually. So it gives you a sufficient condition. Now now we would like to move towards a concrete example. And before moving towards the concrete example, I want to have a closer look at the condition 2 of the theorem that we have just proved and the definition of the gradient flow. Okay, definition of the gradient flow. Because the definition of the condition, when you're going to see that the second condition of the theorem that we just proved and the condition for the gradient flow, you're going to see they are almost same actually, so they are same. So if you have a gradient flow, for the gradient flow, the second condition of the theorems is already satisfied. Okay, so if your flow is not gradient flow, then you have to prove the second condition of the theorem that I just mentioned actually. Okay, we just proved. So if you are talking about gradient flow, don't worry about the second condition of the theorem. Just prove that there exists an absorbing set. There exists an absorbing set actually. Okay. So what we will like to do now, we will like to talk about this concrete problem, the reaction diffusion equation. Okay, with the cubic non-linearity. This is the equation that I am interested in. The equation goes like this: ut equal to plus u plus u minus u cube, where u is a function of x and t, where x belongs to the domain omega, which I'm just going to describe, and